Okay guys, we're gonna go ahead and get started here in just a few minutes. So we left off yesterday going over domain 2.4.2, which again, we're gonna go over PKI to start a class today. And then we are going to go ahead and finish domain 2. And this is gonna be going over cloud technologies. And then finish up domain 2 and then we'll jump into domain 3 as well. Give me 1 second here. I'm teaching. I can't. Okay. Hey, I'm teaching. I gotta go, okay? We gotta put you inside. Because I'm teaching. Yes, I love you. All right, let's go ahead and get started, guys. Sorry about that. I just had to square away my kid real quick, give her some milk so she doesn't interrupt us. All right, so let's go ahead and begin going over domain 2.4.2. Given a scenario, apply security concepts to the design of access, authentication, and authorization systems. And in this section of domain 2.4, we're going to talk PKI and different access control systems. Okay, so here in the red, this is what we're going to be going over. Logging, auditing, and we're going to start off going over PKI, the public key infrastructure. So usually when I like to talk PKI, I like to start from the very beginning and just go over why we have it for the internet. Obviously, we work in enterprises like, in the DoD, where we have a common access card that has an X.509 certificate on there that correlates to our identity and gives us authentication access to our DoD domain. When we talk PKI, though, we like to talk about it on like a global scale. So let's go over when we would use it, why we need it, and why we use it on the internet. So let's say we have a web server here. Let's say this is trepa.com. So on my web server, I want to use HTTPS, which means I want to secure web access to my website. So when a user goes on his web browser and it goes to the URL trepatech.com or trepa.com, I want to have that data in transit connection be secure. So we're going to use something like TLS. So what do I need to do on my web server to make that TLS session happen? And how do I trust? That's a very important thing. How do I trust that that connection is secure? And how do I know that that web server is trusted? Well, we have something called the public key infrastructure, which is pretty much a network of certificate authorities, root CAs, and intermediate CAs that issue certificates to websites, which is really just a web server, that then display that public certificate that we're going to use in our web browser to do this little song and dance called TLS that starts with asymmetric encryption and encryption key protocol like Diffie-Hellman or ECSDA that's going to do secure key exchange, and then symmetric encryption to actually encrypt our data payloads to and from that web server. And that's when we access something via HTTPS. So we want that icon. We want that icon that says our website is secure. We're not going to get this weird error that says, do you want to continue? Connection may be insecure. So how do we start? So public key infrastructure starts at asymmetric encryption. So what we're going to do here is we're going to do like a playbook or a runbook on our web server, which if you're using like Wix or using WordPress, a lot of this is just a plugin that you enable, you put in some information, it does it in the back end. But let's say you're doing SSL cert generation on the actual web server itself in like the Linux CLI. So let's say this server is, Ubuntu, and we're doing an Nginx web service and we're going to run SSL cert. So the first thing we're going to do is we're going to create what's called a public and private key pairs. Now these public and private keys are mathematically combined. And what we mean by that is if one key encrypts, the other key decrypts. So they're mathematically related in that way. And honestly, it's arbitrary which one is the public and the private. It just selects it and then it saves it. So the public key is exactly what it says. It's public. It's there for everyone to use. Now remember, this is asymmetric encryption. So if I encrypt with the public key, I decrypt with the private key. And this is the start of us getting that lock icon, doing SSL, and then being able to do TLS data in transit encryption to all of our users that are accessing our web browser. Okay, so once we do that, this public key again is public. We're going to store that private key somewhere like secure. Could be on like a TPM chip here on our web server or a secure chip, and no one can access that private key. It's local to that web server and it's inaccessible even by the admin. Well, obviously you could go into like if it's SSH you're using or RSA to do this asymmetric encryption, like that's the encryption algorithm you're using, you can probably go find it. It's like /.ssh, it's like a hidden folder directory in Linux, but it's private. It's not supposed to go to anyone. If that private key gets exposed, then it's no longer a secure connection. But okay, so we do asymmetric encryption here. Public key encrypts, the private key decrypts. If the private key encrypts, the public key decrypts. Now that's not the way we're going to use it in PKI, but that's just mathematically how it is related to each other. So we're going to publish that. And now the next step is, well, I still need my public cert, my X.509 certificate that I can post here on my public URL, my public website, so that other users in their web browsers can come to me and say, okay, let me grab that public certificate and let's use the public key in there to start this TLS session. That's our end goal, right? To get this TLS session going. So once I have that, then we're going to do what's called a certificate request. And we're going to build what's called a CSR, a certificate signing request. So we're going to choose an intermediate CA and a root CA to go get our certificate issued to us. So in that CSR is going to be domain information. So that's going to, in the CSR request, our certificate signing request, we're going to have our public key. We're going to have like our OU information, which is like, our domain, things like that. We could also have like some subject alternative names in there, which pretty much just list out, this certificate's going to be good for a bunch of other domains as well. Google does this. If you go look to youtube.com, you look in the subject alternative name on its public X.509 certificate, it's going to be like *.google.com and a bunch of other things. And that's on YouTube. So, which is under Google, they have all these subject alternative names in there. And then just other information, location, US, what region, things like that. Okay. Now, once we have built that CSR, we're going to send that off. And its first step is it's going to hit an RA. So this is like, this RA is pretty much going to say, hey, do we trust this certificate signing request? Before I pass it off to the intermediate CA, do I trust you? This is the registration agent or authority. So it's going to say, do I trust this certificate signing request? And if I do, I'm going to pass it off to the intermediate CA. Now, before I talk about these CAs, before I do the certificate signing request, prior to this, the intermediate CA, something like Cloudflare, one sec, and a root CA, something like DigiSign, already have trust built between each other. This root CA, we'll say RCA, root CA, not root cause analysis there. I know that acronym is root cause analysis, but that root CA and that intermediate CA already have a chain of trust between each other. So prior to this root CA and intermediate CA sign each other's certificates, their certificates that say we trust each other, okay? So once we get past that registration agent or authority, our CSR is going to go to the intermediate CA. It's going to generate a cert for us using the information we sent it, our public key. It's going to hash that. It's going to add over our subject alternative names, any other additional information that we sent to it. And then it's going to send it to the root CA, and it's going to put its little stamp of approval on there too. It's going to sign it and say, yes, I trust the certificate that this intermediate CA is going to build. We're going to send that back. And now the certificate that we're going to get assigned to us over here at Treppa.com is going to have that chain. It's going to say, the intermediate CA issued us this cert, but it was signed and trusted by this root CA. And then the intermediate CA is going to send that back. And now we have our publicly signed X.59 certificate that contains all this information that pretty much has that stamp of approval from the intermediate CA and the root CA. And then we're going to host that publicly, our cert. And now in that digital certificate, it's going to be our public key and the hash, and we're going to be able to use that public key now from the user perspective to initiate a TLS session. Now some more things going on in the background here. So we have that certificate. Awesome. What that pretty much means is that my web browser here, let's say it's Chrome. When I go and download Chrome, baked into that web browser is a list of trusted CAs. So because I'm telling you that the root CA and the intermediate CA are trusted, but trusted to who? To the web browsers. So web browsers, Chrome, Firefox, Edge, Safari, all have baked into it a list of root CAs and intermediate CAs that it trusts inherently, okay? So a big one like DigiSign, like I wrote up there, is going to be baked into Chrome that says, hey, Chrome, when you access a website and you're starting your TLS sessions and you grab a certificate from Treppa.com so you can use its public key to do asymmetric encryption to start that TLS Cipher Suite session, see who it's signed by. And if it's signed by DigiSign, well, guess what? You trust that. So we trust this TLS session that we're about to make, okay? So now we start our TLS session. So what's going to happen is we start our TLS handshake after we already connect to it via IP, and after we do our TCP connection or UDP, then we initiate TLS. So it's like layer 3, 4, and then 5 is our TLS session. That's when we type in that web browser HTTPS. That S means that in the session layer, we're going to do TLS. Without diving too deep into how this TLS handshake works, essentially what we're going to do is we have a public key that we're going to send over to Treppa.com, and then they're going to send their public key back. And then we're going to use the server's public key, and the server's going to use our public key, us being the client, and combine those with our own private keys using something like Diffie-Hellman or ECDSA, and it's going to do secure key exchange. So once we exchange public keys, we're going to combine them with our own private keys, and mathematically, we're going to create a secure key, a brand new key that then we can use for symmetric encryption. So really the steps of TLS after we get our trust down is first we're going to do asymmetric encryption by creating a public-private key pairs on both ends. Then we're going to do secure key exchange, and this is going to be things like Diffie-Hellman, ECSDA. These are just key exchange algorithms. And the math behind this I don't really need to get into, but essentially the server takes a public key from the user, the client, combines it with its private key. The client does the same thing, takes the server's public key, combines it with its private key, And mathematically, we're going to create a key that's unique to our session. The new key, a brand new symmetric key. So then we can do symmetric encryption. And this right here is what TLS is. It's the TLS cipher suite. So a lot of times in TLS, you'll see something like, hey, our cipher suite's going to be RSA, whatever, 2048. That's the asymmetric, using Diffie-Hellman. And then like Salsa 20 for the symmetric encryption. And you'll see that. You'll see that a lot of times like baked into this web server, all the different TLS cipher suites that we have available, which have to match on both ends. So if this web browser is using like TLS 1.2, it's going to have a whole list of different cipher suites, combinations of asymmetric, secure key exchange, and symmetric encryption algorithms that it can combine to do this TLS exchange. And that's it. Then we have our end-to-end encrypted session. That's as summarized as I want to make PKI. Now, on to that trust, that chain of trust. This certificate that gets sent is going to have something called an expiration date, right? So those certificates aren't going to be valid forever. And we're going to have to do that kind of lifecycle management, which a lot of times is automated, and do this whole process again on the server with a certificate signing request to get a new signed certificate that is valid. Now, how do we track the validity of these certs? So baked into the web browser, we're not just going to grab that cert and look at the expiration date. Now, obviously, that is a function that could be possible, but what we have in the public key infrastructure is something called a certificate revocation list or a protocol called OCSP that is going to check the validity of these certs. So when we do a new cert request, that old one should be listed here in the CRL, or we can use this, the online certificate status protocol, that we can use to see if a cert is valid or not. And that is as condensed as I can make the public key infrastructure. To kind of recap the key things here, this CSR, remember, certificate signing request, that's from us, the web server, to our trusted intermediate and root CAs to get a public X.500 certificate that then we can use for our HTTPS sessions. We have a registration authority or agent here that's like the bouncer at the club saying, am I even going to let you get this request to the CA? You know, because there's like bad domains out there that we don't want as in part of our trusted PKI. And then the intermediate CA is going to be issuing you, sometimes it's called an issuing certificate authority, but it's an intermediate CA. And that CA has to get its certificate that's about to issue you signed by the root CA. And there's a prior, what's called chain of trust between these two. So once we get it stamped by the root CA, we're going to issue that certificate to the web server. The web server makes that public. Key thing here needing it's like public key, right? It's what we need. And then now we can start TLS sessions that are trusted. The TLS session is going to first use an asymmetric encryption algorithm. We're going to get the public key from the server. The server is going to get the public key from the client and use a secure key exchange algorithm like Diffie-Hellman or ECSDA. It's like elliptic curve secure something algorithm, forgot the D. And create a new key that we're then going to use for our symmetric encryption. And remember that key that's created in this secure key exchange is unique to only our session because it's combining our private keys, which should be stored locally and not exposed. And then we use symmetric encryption to actually encrypt our data because asymmetric encryption is resource intensive and it's not what you want to use to encrypt large payloads. Symmetric encryption is what we want. That whole suite right here is called TLS. There's multiple versions of TLS, 1.3, 1.2, 1.1. And there's multiple different cipher suites we can use to do that encryption. Some are strong and some aren't strong and some are out of date. Like if you use RC4 for your symmetric stream cipher, guess what? That's not secure. Salsa 20 is like secure. It's just the secure one I can think of top of my head. And then we also have servers over here that are going to host invalid or expired certificates that we can reference to make sure that certificate we're getting from our web server that we're trying to connect to has a valid cert. Okay, so that is PKI on the web. Hopefully I didn't butcher that too bad. Let's clear all these drawings. Let's go back. Okay, just another little diagram here. This isn't like my chicken scratch. That kind of just, goes over this again. Registration authority, issuing certificate authority, but it's also an intermediate, and then the root CA. Awesome. Now, before we move on through the slides that are just kind of going to reiterate everything I just taught you guys, let me bring up Google Chrome, and let's go to our website here. And let's take a look at this secure website just to go over some of those things. So here's that public certificate that I was talking about. Oh, that's not going to let me move in. So here's the issued by. So this was our intermediate CA, Google Trust Services. Okay. And then if we come here to our details, this is Academies. This is a wildcard certificate. So actually, let's go to trepatech.com. Sorry, this will make more sense. Okay. So it's still issued by here. Here's our validity period. And then here's our certificate here. That's like the hash of the certificate. And here's the public key that we give out to all these web browsers. So here's our certificate hierarchy. So there's the issuing CA. And here's some more information down here. There's our public key, certificate. And then baked into Google Chrome, like I was telling you, is a trust already with this issuing or intermediate CA WE1, whatever that is. Let's look at a bigger website here just to kind of further look at this point. Let's look at youtube.com. Let's look at this secure connection. So Google services, right? There's its certificate. And you see it's all the same thing. There's a subject. So it's using elliptic curve public key. There's the actual public key. There's the algorithm that it was used with, signature value, and hopefully you get the point. Now you see these subject alternative names. So pretty much this is saying that this certificate can be used for all these different domains under this organization. So all the different Google like .de, that's like Germany, can use this certificate. That's what we call the subject alternative name. You see there's a lot here, which I don't think my website had like any. Yeah, I don't think it had any, honestly, here. Maybe I should know that off the top of my head. But yeah, it doesn't have any sand. We don't need it, essentially. Okay, awesome. Now, if you ever gone to a DoD site and you type in HTTPS and it goes to the website and then it says not trusted, you have to hit advanced and then you got to go to that site. Let's see if we can do that here real quick, actually. Let's go to like Fort Gordon cyber awareness. I think this just did this to me earlier. No, never mind. I can't find one off top because they've gotten a lot better. Or DoD. Oh, here we go. Okay. So look at this. So does this mean we're not using HTTPS? No. If I did a Wireshark capture here, this is going to be TLS. What this is saying is that the web browser doesn't trust this website's certificate. And that trust just means that whoever issued this X.509 certificate to this website, sts.tradoc.army.mil, Google Chrome doesn't trust it. So if we come look here, it was issued by DoD SWCA67. Now, if we go to the settings in Chrome, hopefully I remember how to do this. Privacy, security, manage certificates. Chrome root store. Okay, here we go. That DoD one isn't there. So remember, this is going alphabetical order. So let's see. This was issued by DoD SWCA 67. That's the issuing certificate authority. I don't see that here. So we're not saying that you're not doing TLS. It's still HTTPS. But we're saying as the client, my web browser Chrome here, does not trust this certificate because it wasn't signed by what Chrome considers a trusted certificate authority. So this is something that you either fix on, well, it's not really even a fix, you really have to. Like if the DoD wanted to, they would just get their certificate issued by any one of these big ones, Global Sign, or these GTS route, or whatever the case may be, okay? All right, now let's go over the slides here. We'll try to just, make this quick because we already went over a lot. So certificate authority. A certificate authority is a trusted entity that issues digital certificates with authenticating content sent from web servers. Registration authority verifies that a user's request is valid by checking domain name and identity. So different certificate types. So we have a wildcard certificate. So this allows an organization to host multiple websites using a single key pair or certificate. It requires that all websites use the same domain name, only the host name can be different. And essentially, we're just saying here, like, we can have subdomains here in that wildcard certificate, and it can be used for both. Subject alternative name, it's a multi-domain certificate. We saw that. It's actually in the certificate itself, like, oh, this will work for all these other domains as well. Client authentication, this is just saying, like, hey, sometimes beyond just web browsers, we could use PKI to actually log into our enterprise, which is exactly what we do here. What we do in the DoD is we have our common access cards, and on there is an X.509 certificate that correlates to our user accounts. Okay, a trusted provider, also known as a TSP, or Trust Service Provider. This is an entity that provides root search to organizations for them to be linked to the global chain of trust on the internet. Just what we saw there, right? All those root CAs, that's a trusted provider. Cross certification. That's when two or more CAs need to trust each other. They will use their private keys to sign a certificate containing the public key of the other. Enables both CA chains to trust each other. Kind of like almost secure key exchange, what I described, but this is between CAs. Something I talked about as well, a CSR, certificate signing request. This is a message sent from the applicant to a registration authority to become part of PKI, to get that certificate issued to them. So lifecycle management, we talk about lifecycle management a lot with data. Certificates are data that we may have to manage, like we do on trepatech.com. You just gotta know when to get new certs, but a lot of times it's like automated. Like if it's expired, hey, get a new one. Certificate pinning, this protects an organization's users or customers from man-in-the-middle attacks. It works by embedding the server's public key into the website or client software. OCSP, a protocol I touched on a little bit. So Online Certificate Status Protocol, this is an internet protocol service for obtaining the revocation status of a certificate. It's just like a CRL, but with the CRL, when we check the certificate revocation list, you have to download the whole thing, and it may be very large, like hundreds of megs, where if an OCS can send a message to a certificate or an OCSP server or service that says, I just need to check trepatech.com. I don't need to download the whole list and search from there. I just need to check it real quick. So that's OCSP. It makes it a little faster. And then certificate stapling. This allows the client to trust the served certificate without contacting the CA for updated CRL independently. And then here's what an X.509 certificate looks like. And we looked at it live, right? All the things that could be part of it. So, okay, so that was PKI. Now to finish up the rest of this domain. So now we're going to go over access control, logging, and auditing. So access control systems decide who should be allowed to access physical or digital resources, but they cannot explain what actually happens after access is granted. Logging and auditing exist to provide visibility, accountability, and evidence of system behavior, ensuring that access is not only controlled but also observable and verifiable. Then auditing is the actual analyzing of log data to determine whether access controls are working as intended. We do auditing and logging for a lot of things in our enterprise, not just as it relates to PKI. This is just, it is part of it. So it is something we have to talk about when it comes to PKI. We need to log our sessions, TLS sessions, maybe on our web server, and audit to make sure that our certificate's still valid, things like that. And then something beyond just physical access control. We're getting away from PKI here. Physical access controls regulate entry to buildings, rooms, or data centers and hardware, forming the foundation for other security controls. When I think of like defense in depth, when I think of protecting an enterprise where we have on-prem, remote workers in the cloud, this is something that, a lot of times cybersecurity, maybe it's not their sole focus. Maybe you have a physical security person for your actual compound, but it's something we have to at least be aware of, that Are our data centers secure? Are we locking them? Is there a badge readers? What kind of badge are they connected to our enterprise, those badge readers? Hopefully not. Hopefully that's an air-gapped system. Are we using biometrics to access a secure area? So we just want to be aware of our common mechanisms to secure our secure spaces, and then also our hardware. Maybe we put cable locks if we don't allow telework, like on our computers, things like that. And we want to make sure we're logging this. So if we want to be able to have, if we're like a badge system, usually the badging server has a log everyone that tried to scan or try to get in an area that correlates to their identity. Logical access control systems. So logical access control governs access to systems, applications, networks. So like if you've been like, this is Wednesday, day 3. We've talked about access control so much, and a lot of it's been logical. When we talked about RBAC, least privilege, it's all logical. So just CompTIA reiterating it a 4th time. You know, you need logical access controls in your enterprise, and you want to have some multi-factor authentication, conditional access, contextual awareness. You want to be able to audit those access controls and making sure we're using the principle of least privilege. So again, just touch on that one more time, CompTIA way. All right, awesome. Let's go ahead and do our quiz. So we are doing domain 2.4.2 quiz here. Okay, so question 1. Let me bring up the Zoom chat. Question 1. A security team is implementing mutual TLS between internal microservices. During a risk assessment, the team identifies that a compromised service certificate could allow an attacker to impersonate a trusted service until the certificate expires. Which PKI feature most directly enables rapid invalidation of compromised certificates in this scenario? So we want to be able to look quickly at which certs are invalid. So there's only 2 ways to do that, OCSP and CRL. So our answer here is going to be OCSP stapling. So a lot of the first paragraph, a lot of fluff to say the real question here is, how do I know if a certificate is valid or not? What protocols do I have? So it's either CRL or OCSP. And this says OCSP stapling because it's very fast. So we're going to go with D. Question 2. An enterprise is designing a certificate-based authentication system for administrative access to critical infrastructure systems. The organization requires that administrators undergo a in-person identity verification and management approval before receiving credentials. That's like the DoD. In addition, downstream authorization systems must be able to reliably distinguish administrators from standard users who also authenticate using certificates. Which PKI design approach best supports this requirement? All right, this looks like a tough question, honestly. Okay, so we want to use certificate-based authentication for our standard users and our administrators, and they must do in-person identity, and they must be approved by management. Like they must have a sponsor to get those credentials and those certificates. I literally just did this. I got my CAC reissued at our Deers here at Fort Bragg today. And I had to get sponsors, right? My GS14 employee, or not mine, but the GS14 on the program. Okay, so issue administrative certificates from the same CA as user certificates, but configure a shorter validity period. Probably not. Use a dedicated certificate template with strict enrollment and policy constraints for administrators. That's probably going to be it, because if we want to differentiate, let me read the rest. Use OCSP stapling to validate administrative certificates during authentication. No, that's not what OCSP does at all. So we can rule out C. Store administrator private keys on a different certificate authority than user certificates. Well, private keys are going to be secure no matter what. So it's not going to be D. And I guess, I say OCSP, that's not what it's built for. I mean, I guess it could be used in that way. But that's not going to be giving us what we need here, which is just separate, right? We need users and administrators to be separate. That's pretty much what the question is saying. So we're going to go with B. Use a dedicated certificate template with strict enrollment and policy constraints for administrators. Yeah, that's why you guys hire Trepa, because I'm military, so it relates. I can relate it better to you guys, especially like when I teach soldiers. Like I pretty much have to talk Army to them to get them to understand any cybersecurity shit. All right, question 3. An organization uses internal PKI to issue device certificates for corporate laptops. These certificates are used for Wi-Fi authentication, VPN access, and device posture enforcement. A security engineer wants to ensure that if a laptop is stolen, access can be revoked immediately, even if the certificate has not expired. Which PKI architectural consideration is most critical to achieving this goal? So this is actually leveraging like probably internal certificate authority to actually do what we call 802.1x and then WPA3 enterprise. So if you ever use Wi-Fi, like if you guys ever are in a CSFC environment and you use like Wi-Fi for like SIPR or anything like this is actually going to be similar to what you do, minus the VPN. Well, no, VPN access, right? For your Wi-Fi, is you're going to have to integrate it into your certificate authorities and stuff like that. But okay, sorry, let's look at the answers. So A, ensuring certificate templates use strong encryption algorithms. Okay, so we want to make sure access can be revoked. So, I mean, encryption, yes, we want strong. C, designing reliable and reachable certificate revocation infrastructure. Probably is what we're going to have to do, because if you guys have ever deployed Microsoft certificate authority services, I have a buddy that works at MTC, and he says you guys have your own internal network that you have to go through ATO processes here at Fort Bragg. And I'm assuming you may have like an internal one that you have to manage. You know that like CRL and all that stuff is like kind of hard to like, sometimes it gets forgotten about in an internal one. Okay, you guys don't have, yeah, he said they have their own like training network here that they have to manage. That's like not necessarily like NIPR or like other classified networks, but yeah, it's going to be C. Designing reliable and reachable certificate revocation infrastructure. Yeah, that's the key word there. You're definitely right, Masood. All right, awesome. 100%, guys. Let's go. Okay. Damn, I talked for a while because I talked for like almost 40 minutes. All right, let's take a quick 10-minute break. Let's refresh. I know PKI is always a long one for me. I think it's because I get excited about it because I've actually dealt with it a lot. But yeah, I wonder. I was actually at Fort Carson at the MTC supporting Next Gen C2 at my old job, and the MTCs that I visited, you guys all have like the same exact building. It's so funny. But yeah, they had their own like training network too. They had a lot of shit going on. But okay, sorry. Let's go ahead and take a break. 10-minute break. Let me put my timer on, and then we'll come back. We'll finish up domain 2. Okay. thing's funny? I go on water breaks and I work out in my home gym. You can come in the frame. Only 5 people are watching. Maybe they can come in. Huh. If Juji's still asleep, I can make it work probably.
Give me that. Daddy, we do.
I'm working out, honey.
By exercise. I mean,
What?
a race car.
Your race car?
Yeah, okay. They don't want the. No, that's like heavy. That's heavy, Dad. That's heavy.
It's really heavy.
Yeah, but go get it for me. Go get it for me, Daddy.
Your race car's right there, honey.
But I keep rubbing.
Why?
But it's too heavy for me. You can rub it.
You got it.
No.
You got it.
No. No, I know. Just careful. Daddy.
Honey,
Just careful.
I'm careful. Let me work out.
No, I can't hold it. I can't hold it.
What do you need?
I can't hold it. I don't know how it works.
There you go. Mm-hmm.
That's too heavy, Dad. Too heavy. It's too heavy for me, Dad. Too heavy. Too heavy. Too heavy, Dad. It's too heavy. Daddy, take it in the living room in the morning. Mommy, mommy.
Come on. Okay, get up. I'll take you to the living room.
That's good.
Amelia was walking around with it. I thought she took it back inside. Oh, it's right here. Put your legs straight. Oh, sorry. Why don't you want me in the live stream? Okay.
She's too much. It's a little bit smack too.
Okay, we're gonna get started again here. Let's do it. Okay, let's go ahead and get started again. So now we're gonna go over domain 2.5. So domain 2.5, given a scenario, securely implement cloud capabilities in an enterprise environment. We're gonna go over serverless and cloud-centric technologies here. Very important section because the cloud is actually quite a big, well, it's an attack surface. It expands your attack surface and we need to know how to lock it down. And a lot of times that starts with just cybersecurity fundamentals again, starts with IAM, identity access management, but then also looking at all the microservices that you may have, all the services running that have something publicly exposed or something that could be exploited. A lot of times we're looking at API security here. So let's jump into it. So these are our objectives, and we're gonna do everything in red in this first slide deck. So the first thing we're gonna talk about is a CASB or CASP, so a Cloud Access Security Broker, a very common technology implemented by enterprises. Sometimes you don't even, not that you don't realize it, but maybe your Palo Alto firewall or some sort of like load balancer might do some of this for you. There could be a CASB that sits like in the cloud that, they may not call it CASB, but it's a lot of these security functions that you may get in like Azure or GCP. That's what I always reference. That's what I know. I don't know anything about AWS. So I know maybe some of you maybe know AWS, but I know Azure and GCP. And a lot of times those cloud functions carry over just with different marketing and brand names. But okay, so what is it? So a CASB or Cloud Access Security Broker is a security solution that sits between cloud service consumers and cloud service providers. Fancy word, we're saying your employees and the cloud. And where do we sit and how do we build some sort of cybersecurity functionality in the middle there to protect our traffic and to secure our resources? So its primary purpose is to enforce an organization's security policies whenever users or systems access cloud-based applications or services. That last sentence here in this first bullet point is probably the most key thing when it comes to like the exam. It is there to enforce an organization's security policies that they may already built on-prem and extend it to the cloud and give you some visibility, monitoring capabilities into what your users are accessing in the cloud, maybe before they even get there or on their way back from their cloud services that they need to access. So in traditional enterprise environments, security controls are deployed at the network perimeter. We've talked about this, how in traditional environments, you had this nice little moat. You imagine your enterprise as our HQ building. All the users come into the HQ building. This is before telework, and they log into their domain joined computer. All the group policy is applied, and anything external that they're reaching out to the internet has to go through our proxy server or our firewall or load balancer first, and we have that visibility, and that was it. So we kind of knew where the exact perimeter is and where to focus security. But now in our sprawling enterprises where we have remote workers, cloud-based services, that extends our perimeters and introduces a lot of different attack surfaces that was the challenge, was how do we gain visibility into all that in a single place where we don't have cyber administrators looking at the cloud, looking at our on-prem firewall, looking at the VPN concentrator and the MDM solution, all these different places for potential vulnerabilities. So again, with cloud computing, this just disrupts that model. Users may access cloud services directly over the internet from remote locations or unmanaged devices. So the CASB is one of these security functions or hardwares or softwares that restore that visibility and control by acting as a centralized enforcement point for cloud usage. And it allows security teams to see which cloud services are being used, what's going on with the data that's being processed, and to ensure that it aligns with our organizational policies. So a type of CASB, API-based CASB or CASB. So an API-based CASB integrates directly with cloud service providers using their published application, their APIs, application programming interfaces, instead of inspecting live network traffic. So the CASB communicates with the cloud platform itself to retrieve information about user activity, stored data, permissions, and configuration settings. So it's kind of like, not that it's almost reactive. It could be, in line. And what I mean by that is, yeah, users may access the cloud, but then that CASB and the API model is still reaching out to say, okay, what's my user doing? What's my user doing? So maybe the user doesn't interact with the CASB directly. It's, out of band from that live connection, but we're still getting some visibility into there. And then since it's API based, that gives us what? Some sort of permission, some sort of like credentialed access into our cloud services to maybe apply security to it. So because API-based CASBs operate out of band, they do not sit in line with user traffic. They don't introduce any latency or require complex network routing changes, and they're effective at performing deep inspections of cloud environments. So let's leave this last section here. So API-based CASB may scan files stored in a cloud collaboration platform and detect sensitive information that violates company policy. Kind of doing like a DLP almost function. I talked about this yesterday where DLP in the cloud and on-prem, really same function, just the tools that we use in the cloud may differ, where this CASB can scan those files and look at things in your cloud instances in your tenants and say, whoa, that sensitive information shouldn't be there. That should be in our secure on-prem storage, not our cloud base. Okay, and then a proxy-based CASB. So this is that inline CASB. It makes a little bit more sense, I feel like, when we teach this. Maybe I should switch these slides around. But a proxy-based CASB kind of acts like that proxy server. Remember that forward proxy server where it's in front of the users? Users connect there and it does like public address translation, deep packet inspection, maybe some URL filtering, and then sends you off to the internet. So it's like, nope, you hit here first before you head out to the internet. Like F5 does this, things like that. This is for the cloud now, proxy-based CASB. This could be an actual server that sits and then you virtualize the CASB service. But it operates in line. It intercepts traffic between users and cloud services. And this allows it to inspect and enforce security policies in real time. So they can be deployed as forward proxies, where user traffic is routed through the CASB before reaching the cloud, or it could be reverse proxies. So like I said, there are some like security functions native to a lot of our major cloud service providers that kind of act like that reverse proxy that say, you know, we're going to deploy this resource in my Azure tenant that's going to act as this kind of proxy to do that packet inspection before it gets in. Now, when we deploy VMs, we put them in a VNet, we do like a NAT gateway, load balancers, and then we can add like network security groups to that. That kind of almost functions like that reverse proxy CASB without calling it that. So because they operate inline, proxy-based CASBs can block unauthorized access, prevent data leakage, and enforce authentication requirements immediately. Okay, we talked about shadow IT a lot. So shadow IT detection. So this happens in our cloud as well. You think about the public cloud. And if you don't do your IAM policies correctly, because it's almost like system administrators, once the cloud was introduced, it was like, oh, here we go. It's like a whole nother domain to manage. And then we started hiring cloud engineers. And then we started hiring cloud security architects that pretty much were just labeled that. But they were like, hey, IAM policies, enforce them. Make it work with all of our different SaaS and PaaS, right? But shadow IT can exist in the cloud as well. So employees often adopt cloud tools that increase productivity, collaborate more easily, or solve business problems quickly, but they may not meet our security or compliance requirements, especially if we're in a public cloud and we give users access. That also messes up something called FinOps, like financial operations, if you allow that, which, you know, no one should be doing that. So shadow IT also happens in the cloud. All right, we talked about this a little bit in the RACI matrices, but RACI matrix is kind of more just like from a holistic view, you can do it for anything. But the shared responsibility model is something specific to our cloud service providers. I kind of talked about this already, but we'll go over it again. When we're dealing with a CSP, cloud service provider, they are allowing us access via a portal to cloud data centers for us to deploy resources under our cloud accounts, under our cloud tenants. That's what they're allowing us to do. And there's some basic service models for that. Infrastructure as a service, platform as a service, and software as a service. And then there's things like functions as a service, database as a service. There's a lot of things as a service now. It's almost like, I hate that it's almost becoming a marketing term, but originally you look at the NIST publication for cloud. Oh, I don't remember the publication exactly. It's gonna bug me. But it talks about these service models and deployment models, the basic ones, IaaS, PaaS, PaaS, and SaaS. Okay. So since the cloud is allowing us access to their data centers, there's things that the cloud has to be responsible for security. At all levels, at all service models, that's the data center's physical security, power, and the ability for us to do IAM. That pretty much happens at SaaS, PaaS, and infrastructure as a service. So like account and identities. Now, you have customer responsibilities. So before breaking these charts down, what that means is if I deploy a VM in the cloud and I give it a public IP, and that's it. I leave it there. I leave this Linux box running with the public IP, and I don't harden it at all. I don't block any sorts of ports or protocols. And a hacker exploits that VM. Is the cloud service provider at fault? No, it is not. You went into a contract with that cloud service provider that said, I'm going to allow you to deploy a VM. I'm going to give you the compute, the storage, the network resource, but you have to configure it. That's on you, the customer. Same way if you went and bought a server and then it got hacked, would you be calling up Dell saying, yo, you need to fix this? No, you wouldn't. So the cloud may be able to tell you when something looks fishy because they don't want like just, from their infrastructure, these torrents or these different attacks happening, denial of service attacks originating from them. So they may send you an email saying, hey, this looks suspicious, you need to fix it. But any costs that accrue from that, it's up to you. It's your responsibility. Now, if we're doing PaaS, platform as a service, the cloud provider has a little bit more responsibility because we're saying we're giving you a platform to deploy code on. So a lot of that underlying operating system, the cloud service provider will patch and will manage. But as far as the application goes, the actual application you're deploying, that's on you. And then software as a service will be, a lot more responsibility on the cloud, but you still have some things. So you still, as the customer, say, hey, I need to still do IAM. I still need to manage my devices that are accessing that software as a service. But the cloud does the application management, it does the middleware, the network controls, and the operating system. So that's what the shared responsibility model is. And you have to understand that when you start using the cloud, especially if you're using the public deployment model and you're working in an organization where they expect you to manage infrastructure in the cloud, that, remember, it's a pay-as-you-go service model. It's operational expense. If one of your things gets exploited and it's doing like network egress traffic originating from the cloud, that racks up a huge bill. So be careful when you're using the cloud. Do I need to go over any of these bullet points? No, I think that's okay. Yeah. And on screen here is, this is Azure, Microsoft, and then that's AWS below. I don't know why it looks so crappy here. I probably should change that image out. Okay, CI/CD pipeline security. We already talked about this, but guess what? CI/CD operations still happen in the cloud, especially when we're developing in the cloud, because a lot of times web applications get automatically deployed to the cloud. You need to be part of that DevOps solution and implement security at different points in your pipeline. So a continuous integration and continuous deployment pipeline automates the process of building, testing, and deploying applications. I can read this next slide. If an attacker compromises the CI/CD pipeline, they can inject malicious code directly into production systems. So just saying, like, whatever step you're in that pipeline, whether you're a platform engineer, a site reliability engineer, a DevOps engineer, a cloud engineer, and you're engaging with the DevOps team or you're engaging with the IT operations side of the house, you need to make sure that you're inserting the sec into DevSecOps, and that at whatever stage that's at, whether it's verifying, the configure stage, the detect phase, the staging phase, that you're looking at third-party libraries, you're doing your static analysis, you're putting that web application maybe in a runtime environment in kind of a closed-off private cloud model to then try to attack it, try to do some API denial of service against that application to see where the weak points may be. All right, now we're going to go over different infrastructure as code tools here. Really, like, there's scripting languages, coding languages, I guess you could call them. Terraform's not really coding, but it says tools here. So Terraform is an infrastructure as code tool that allows organizations to define cloud infrastructure using declarative configuration files. Let me break that down for you. What we're talking about here is that from your administrative platform, whatever that is, wherever you're deploying this Terraform code, you're hosting it in GitHub, and then you're executing that Terraform file against multiple different cloud instances and cloud service providers and tenants. This is a tool that allows you to interact and deploy infrastructure at a scalable way that gives you that scalability. So if you want to be a cloud engineer, a high-speed cloud engineer that isn't just doing click operations into a cloud portal, you want to learn something like Terraform, where you can make your Terraform files and say, hey, we're going to deploy all these things in our GCP and Azure instances all at once from a programmatic way. Now, from a security standpoint, Terraform improves consistency and reduces configuration drift. What we mean by that is if we have a standard of how we deploy let's say, storage accounts across Azure, we make a single Terraform script that says, hey, whether it's in the East, West, or EU region, we're going to deploy this storage account with these types of storage, like we're going to do cold, archive here, here, and there. We keep that template consistent so that we don't have the human error or configuration drift. And when we do revisioning and upgrades, instead of going into each instance individually and updating it, we update a single file that reaches into all of our regions and all of our cloud instances. But where's the security in this? One, wherever you're hosting this file has to be locked down, so you're hosting it on GitHub. If you need keys for this, like API keys, you don't want to store them directly into the code. You want to put them in some sort of key vault. You want to do maybe some code signing on any of your infrastructure as code, like main branch, to make sure that it hasn't been tampered with. All right, Ansible. It's another configuration management tool, an automation tool. Now, you may ask me, so what, what's the difference between the two? Well, Terraform, I don't want to dive too deep into it, but Terraform was really built for like cloud. Now you can use Terraform on anything. You can use it in like ESXi. You can even use it for networking now, for networking devices. But it was originally built to give you that single state from multiple different vendors. That was the beauty of Terraform. Where Ansible was built originally by Red Hat Linux, it's SSA based, and it lets you just SSH to any clients that are defined in your Ansible configuration file or host file really, and it lets you execute code against it. So like in the networking field, that's where I'm in, we use Ansible to automate network configuration, and really we're just from our Ansible like managed server, which is really just a Linux device that I say, Ansible playbook, run this YAML file. It allows me to do a show run command to 20 different routers, and then I can get that output back. Or I can use Ansible to script it and save that in some sort of like file share, or put it to a Slack message, or export it to HTML and upload it to a SharePoint portal, however I do it, right? But Ansible was originally just like simple SSH management using the same, language of the device you're configuring. So if I get Cisco, it's still gonna use show run. If it's a Linux server and you need to install Apache, you're still gonna send a command via SSH apt install Apache, right? Okay, package monitoring and container security. So now we're talking about how do we, basic security for our containers and package monitoring. So modern applications rely heavily on third-party software libraries and dependencies. Package monitoring involves tracking these dependencies for known vulnerabilities, malicious code, and license compliance issues. Now containers package applications and their dependencies into isolated units that run consistently across environments. So when we deploy a Docker container, we go to the master library in Docker, we download that container image, and we know that it's safe because it's coming from a reliable source. So when we deploy containers and container images, we want to make sure we're getting it from a reliable source, but we also want to make sure we're using fundamental cybersecurity. The networking for our containers, if we're using an orchestration tool like Kubernetes, we don't want to expose our cluster to like a public IP. It's just the basics again. But beyond that, the container image is still running like a Linux in there. There may be some simple hardening on our containers that we may want to do. But the great thing about containers, guys, is if one gets exploited or exposed, it's easy to delete and then download that container image again and then deploy your code straight to it. With a cluster, obviously you may be worried about if one container gets exposed, then do we have that east to west filtering? Do we have the, that zone kind of traffic filtering between our containers? We have to worry about that as well, but the great thing is how quickly we can deactivate and then rebuild clusters. Okay, then container orchestration. So container orchestration platforms manage container deployment, scaling, networking, and availability. These platforms introduce additional security risks due to their complexity and central role in application environments. What we're saying here is that if we're managing containers using Kubernetes, and this Kubernetes orchestration tool has access to our Docker containers directly and access to our cloud platform, which we're using as like our compute and storage to deploy these containers. If this gets exposed, what else is exposed? It's just an increase in attack surface again, and the basic security still applies. Good IAM, multi-factor authentication, things like that. And then monitoring. We don't want to forget, just because we have this new fancy technology where we deploy containers left and right, Do we forget about logging, monitoring, and auditing? Of course not. Okay, serverless computing. I love this name. I don't know who came up with it, but what this means, when we used to deploy code, a web application or application back in the day, we managed the full stack. So maybe it was a system admin, but you buy a server, maybe a couple servers, maybe virtualize, make VMs, but the database sat somewhere, had its own IP, and that back-end application logic would interact with our database, but maybe we'd separate them, maybe on different servers. Maybe it was all centralized. And then the front-end code would also sit in like an index file, right? The Etsy/www, and it'd be index.html, and that'd be the front end. And then when a user came to our web server, it would get that front end, we'd send requests to it, REST API to log in, JSON down to the back end, API exposes to the database, and it'd all be on that one server. So obviously, beyond just knowing how to code and to make a nice application, we needed someone there to manage that server for us. So you can kind of see where I'm getting at here with we need to scale, and deploy quickly. What solution did they come up with? Serverless computing, where they said, you don't need to worry about all that. You can just deploy your code. We're going to build a data, and this is in the cloud. We're going to deploy databases for you, have these functions for your backend, and have this API gateway so you can interact with us, and you don't have to worry about any operating system underneath. Now, obviously there's still going to be some sort of Linux or something underneath to host, but you don't have to worry about it. That's serverless computing. That's the beauty of it. You just deploy your code and forget about it, right? And that's it. So this kind of differs from what we would call monolithic web architecture, where we had things on a single web server. So serverless computing abstracts infrastructure management away from developers, and code is executed in response to events, and the cloud provider manages scaling, availability, and underlying resources. Yes, there's still a computer somewhere, right? There's still a server somewhere, but it's abstracted to you. You don't care, you don't know about it, and you shouldn't need to know about it. You're just deploying code. That code's compatible with this serverless environment that you're interacting with, and that's it. Now, security, right? This is a security course. I'm a student, code as infrastructure, or infrastructure as code. Yeah, that's the future, not even the future, that's the now. You go apply to be a system admin somewhere in like private sector, you're pretty much almost quasi DevOps now, right? There's still some separation in there, but yeah, so what do we have to worry about? The things that we still may have to manage in there, like our databases, this Azure functions here, it's just for like backend and like API gateway. We still need to maybe put some rate limiting on here, some sort of security. Again, when you're interacting with the API, don't just expose the API key and like your code on your public GitHub, things like that. Oh yeah, API security. So application programming interfaces are a foundational component of modern cloud architecture. APIs enable communication between services, but also represent a major attack surface, of course, because it might be public. Authorization ensures that only properly authenticated and authorized entities can access specific API resources or actions. Think of like OAuth 2.0, OpenID Connect, which has like this back-end trust already built between maybe an API client that's going to be reaching out a lot, and you have to configure that rather than just some random trying to connect to your API, just sending API keys that hopefully it gets in. So the API rate limiting, logging, we need to log our APIs and say, hey, who's actually accessing it? Do we see any suspicious behavior? So logging is essential. And then rate limiting. Rate limiting protects APIs from abuse and denial of service attacks. All right, quiz time. Let's do it. Oh, what happened here? Okay. It's on my other screen. One sec. Okay, we're going to be doing domain 2.5.1 quiz. One sec, guys. I'm just moving my desk up here. I want to stand now. Okay, question 1. A development team uses CI/CD pipeline to automatically build and deploy applications to a cloud environment. Management is concerned that a compromised pipeline could allow attackers to insert malicious code directly into production systems. Which security practice most directly reduces this risk? Okay, so we're worried about someone getting into our pipeline and inserting malicious code. So where does that start? If someone is able to get into our pipeline, which is really just a GitHub repo and some platforms that we're managing, which is like servers, think servers, even if it's in the cloud, cloud services. If someone's able to get in there, what does that mean? They were granted access by somebody. Whether that's, bad key management, bad password management, whatever the case may be, they got access to insert that malicious code. We're not, in this scenario, I don't think it really describes insider threat or like someone downloading, so falling victim to like phishing attack. So I think it's our access. So let's go ahead and look at our answers here. Encrypting data at rest in cloud storage, we do that. That's not necessarily part of the CI/CD pipeline. Deploying a container orchestration, no. Implementing strict access controls and auditing for CI/CD pipeline components, that's probably gonna be it. Let's look at D. Using serverless functions instead of virtual machines, that has nothing to do with this. So I'm gonna go with C. Yep, you guys are right. Implementing strict access controls and auditing for CI/CD pipeline components. Okay, question 2. An enterprise deploys serverless functions that access cloud databases and messaging services. A security review reveals that the functions have broad permissions that allow access to many unrelated resources. Which security principles should be applied to most effectively reduce risk in this scenario? So we're worried about functions, access again. And like I said, it's funny with the cloud. I watched this trainer on YouTube called John Saville, and he talks about this, where when we looked at like core functions of the internet and computers, it was always the networking, the compute, RAM, CPU, GPU, and then our storage, our solid state drives, our actual storage drives. In the cloud, he talks like how IAM is the new, that's the new surface. That's a new fundamental of computing now with the cloud being introduced into everything. And it's true. Pretty much all this security we talk about in the cloud, where does it start? Don't give someone access. Don't give someone access. It's not even talking about anymore like a hacker like brute forcing passwords, because we have so much passwordless authentication out there now and multi-factor authentication, contextual awareness. It's like you need strong access control, strong IAM to protect your cloud. So yeah, D, right? D. I would have taken A too. You always need good defense in depth, but yes, principle of least privilege. Even in serverless functions, even in a serverless environment, you still need good IAM. Question 3. Let me type it up over here 1 second. An organization is concerned that employees are using unsanctioned cloud applications to store and share sensitive business data. The security team wants a solution that provides visibility into the cloud, so we're CASB, usage, and can identify unknown cloud services without requiring changes to user traffic flow. So it's not going to be inline. Which solution best meets this requirement? Oh, wow, this one, confusing. Well, not really, right? But it's A, right? Because we don't want to interrupt traffic flow. We want visibility, but anyways, that's fine. Yeah, A. Obviously, it's between A or B, but because this keyword, without requiring changes to user traffic flow, it's going to be A. All right, awesome. So that's another 100%. Guys, we're going to take a quick, I'm just going to put 8 minutes up here. I got to go pee, and then we'll finish, okay? Sorry about that. I know I'm taking a lot of breaks. We've got to get through a lot today, so just give me 8 minutes. We'll come back, okay? Come on, Gigi. Come on, Gigi.
I feel baby.
Gigi, we're going to the car. Come on.
No, that's it.
Come on, Gigi. Okay, let's go ahead and continue. So now going over domain 2.5.2, we're going to go over cloud security strategies. Okay, so here is the objectives we're going to go over. So encryption keys. So just like on-prem or really anywhere we find cybersecurity, we have encryption. We have encryption in the cloud as well, where we encrypt like our disks in the cloud. Different than like storage accounts where it's actually like disk drives we may attach to virtual machines. We can do full disk encryption on that in the cloud as well. So in cloud managed encryption, the cloud provider generates, stores, rotates, and protects encryption keys on behalf of the customer. This approach simplifies management and reduces operational burden, so organizations don't have to take on that burden themselves. We have to maybe host their own HSMs, those hardware security modules that host all these different encryption keys that they may use. In customer managed encryption, the organization retains full control over encryption keys. Keys may be stored in a customer-controlled key management system, a hardware security module, or even on-premise infrastructure integrated with the cloud. So you could deploy like an HSM in the cloud. That could be a resource that you manage in the cloud, and that would be considered like customer managed encryption because you are deploying that resource, and then you have to manage it. You have to, create your own encryption algorithms. And I don't mean like you invent one, but you select, AES 128, whatever the case may be. Okay, moving on. Licenses. So licensing in the cloud is very important as well, especially like you see here I have licensing in Azure here, but a lot of like advanced security features that you may get in the cloud may be a license you have to pay for. So in Azure, there's something called P1 and P2 licensing for Entra ID, and that P2 license allows you to do something called conditional access, which gives us that like contextual awareness that we want when doing IAM and enforcing multi-factor authentication when we see something like suspicious. So licensing in cloud environments also introduce security and compliance considerations that do not exist in traditional on-premise models. I'm going to differ a little bit there. Licensing is a big pain in the ass on-prem or even in the cloud. Like if you work in a Cisco environment, you know how licensing can be annoying. You don't have that network advantage license, you don't get 500 megs, or you don't get the right one, you only get 10 megs. You don't get the right license, all of a sudden these advanced IPsec encryption tunnels can't be used. So it's the same, right? I mean, but there's just more licensing in the cloud. Licensing is like a whole subject, even like in the Azure cloud cert like track. So, it's important. It's important we keep track of licensing. We still do the managing of licensing in the cloud that we would do on-prem, where we have like an inventory of them. In customer managed licensing, often referred to as bring your own license, the organization is responsible for ensuring the licenses are valid, properly assigned, and compliant with vendor terms. So this is how I've always done it on-prem, where, we use the ESXi. That's the type 1 hypervisor I've been used to using. And we would manage the ESXi license. So if I put it on a server, that one-time use license, and I try to use it on another one, it didn't work, that's my fault. And I have to go to the vendor and ask for more, pay more money. So the cloud could also be like that, where you buy 10 licenses and then you assign them as you see fit. Or there could be a deployment where you just say, hey, maybe money's no problem, and you say every new user in this environment gets a license automatically. I don't have 20 users and I have 10 licenses. You don't have that weirdness where like if the cloud just does it automatically for you. But there's multiple ways you can do this. It really just comes down to your organization, how you want to assign licenses, how you control and manage them. Cloud data security. So let's talk about data exposure and leakage in the cloud and how it may differ from what we learned on-prem. So data exposure occurs when sensitive data becomes accessible to unauthorized users. That don't change whether it's on-prem or in the cloud. Now, why is this different? Because again, the cloud is really a data center that's managed by that CSP, and they give you portal access. So there's multiple different deployment models we can have: private, public, and hybrid. Now, in the public cloud, that is a multi-tenant environment. And what we mean by that is, if I log in and let's say Jeremy logs into the cloud, we could be deploying resources in a Azure East 1 region. And I could have a VM in the Azure region under the VNet in the Azure East region, and he could have a VM in the East region in Azure as well. And possibly that VM's whatever operating system's code could be isolated, but on the same exact physical server. So it's multi-tenant. So with data exposure, the public cloud may be something that is a compliance issue. We may have this compliance that says, hey, no, our sensitive data can't be in a public cloud environment. I don't care how much IAM policy you place or how much rollback access control you place. That's a multi-tenant shared environment. We don't want that. So other things could be exposed APIs in your public cloud deployment, where you're exposing things publicly because you're just deploying resources, getting something to work, and you don't realize like, hey, that actually exposes us more than I'd like. So like improperly configured APIs. And guess what, guys? Guess what? All this in the cloud is controlled by what? It's secured by what? Your IAM policies, the permissions you set. Because a lot of times you deploy a resource in the cloud, it gets its own little service account. And then you can apply permissions on that service account. And then if that's not protected properly, could lead to data exposure. So data leakage refers to the unauthorized transfer of data outside the organization. So your organization will have their own cloud tenant, and if there's sensitive data in there that you don't want getting leaked, or maybe there's a process, there's proper channels to get that information off the cloud into someone's like personal computer, and if you're not going through those proper channels, we call that data leakage. So this may occur intentionally through malicious insiders or unintentionally through compromised credentials, insecure integrations, or vulnerable applications. Okay, cloud data security, data remnants and insecure storage. So data remnants is the residual presence of data after it has been deleted. In traditional environments, physical destruction of storage media mitigates this risk. But what can we not do in the cloud? Well, there's some things we can do. Like Azure has a program where you can buy terabyte drives, put whatever you want on them, send them to the cloud, and then it's yours, and then you can get them back. But anyways, data remnants was something on-prem we could easily fix. When I say easily, we had to destroy it. We had to degauss hard drives. If it's a solid-state drive, destroy it, shred it, whatever the case may be. You can't do that in the cloud. You can say delete, and it can delete, and then the cloud data center, if it doesn't get hacked, you're fine, but it's not something we can ever be sure of that data is completely gone. So the cloud providers, it's up to them. Essentially, we're placing that responsibility on them to ensure that they have secure deletion mechanisms, and we must understand our data lifecycle management and how we do that within the cloud. And that could just be, hey, right click, delete. But if we do have that sensitive data in the cloud, we want to make sure we're doing the proper controls again. Encrypt it, and if we're deleting it, we delete it in the cloud, and then that's pretty much it. There's really nothing else we can do. But then in the cloud, we may have these things or these policies on storage accounts that say, oh, you can reactivate this in 30 days after deletion. So it gives us a little bit more control like that. Insecure storage resources. So cloud storage services are a frequent target for attackers due to their accessibility and high data density. Insecure storage resources include unencrypted disks, publicly accessible object storage, and storage systems without proper access logging. Secure implementation requires encryption at rest, strong identity-based access controls, and logging of access attempts, and regular audits. It's so funny. Is that any different than what we do on-prem? When we have storage on-prem, what do, guys? We do full disk encryption. We make sure there's permissions set properly, and we make sure we're logging, and we make sure we're doing backups. You're going to do those same principles on the cloud. It just gets done differently with different tools. When I say differently, it's just you're not getting into a NetApp storage area network now, or maybe you're on the NetApp portal CLI. Now you're just in the cloud. So maybe you're building Terraform, you're using Python, Ansible, or even the internal Google Cloud Console or the Azure PowerShell console to do all this configuration of access control and encryption and logging. And in Azure, you want to log, that's Azure Sentinel or Microsoft Defender, I think they call it now in the cloud. Okay, cloud control strategies. So we have proactive, detective, and preventative. I didn't put preventative up there in the title. I probably have to change that. But proactive controls are designed to reduce risk before security incident occurs. In cloud environments, this includes secure architecture design, standardized deployment templates, and policy enforcement. It's so funny. We probably went over this already, different controls. We have preventive, detective, compensating controls, and it's you learn it. But now since we're talking about the cloud, you learn it again. It's it means all the same thing. We have proactive controls on-prem, we have proactive controls in the cloud, and maybe, again, we just implement that a little differently because it's something we may not control. We may have different service models in the cloud, where on-prem we know we have that Cisco UCS chassis. Anyways, so examples of this include using infrastructure as code with built-in security baselines, enforcing encryption by default, and requiring multi-factor authentication for administrative access as a proactive control. Where we assume the breach, that zero trust tenet, we always assume breach and then never trust, always verify. We do that on-prem, we do that in our cloud environments. Detective controls. So detective controls identify security events that have already occurred or are currently happening. These controls are essential in cloud environments. So a lot of times the cloud provider will will give you access that you still have to configure and set up yourself to monitoring tools in the cloud. So they have logging and intrusion detection systems kind of built into the cloud that you still have to set up. Or you could integrate a third party. You could do like Splunk could technically monitor and log cloud instances if you would like. Preventative controls. Preventative controls actively block unauthorized actions. So what's a preventative control we just learned about that we can implement from users to the cloud? CASB, like an inline proxy CASB. What other preventive controls can we have in the cloud? This isn't a rhetorical question. It's IAM again, Identity Access Management, like we've been talking about. In the cloud, we also configure network segmentation. It may look a little different. It may not be VLANs, or in Azure, we have things like VNets. I know in AWS, they call it VPCs, where we have our own subnets. We have a big subnet, we build our own subnets, and then apply security controls against those subnets, and then place resources in that subnet. So then that VM or that container cluster or whatever the storage account is part of that VNet subnet that has those application or network security groups applied to it. It's like an ACL or firewalls. And then again, IAM, conditional access controls. Customer to cloud connectivity. So if we read the NIST publication of the cloud, like let's just go to it. Why not? NIST Cloud SP. I should know this one. I've read it a few times. 2011, yeah, that's fine. If you read this, customer to cloud connections. Here's the essential characteristics of a cloud. You see this broad network access? So when the cloud became a thing, like even like if you think about a VPS, a virtual private server that you could rent, those have been around a while. The point was you can access it from anywhere. So I love this slide that's like customer to cloud access. Well, the cloud's access has always been customer focused because the whole point has been deploy your resources here, guys, because your employees, your customers, whatever, can access us. They just need internet. They can have a 3G connection. They could be able to, well, maybe 4G, to be access our some SaaS appliance, right? So what we're talking about, we go back to this slide here. I think what this is trying to say is like the enterprise. Not necessarily just, we know the cloud is supposed to be accessible over the internet, but we have private cloud deployment models now. We have public cloud deployment models that maybe we want a little bit more security. Maybe we're saying like, hey, we don't want you just to be able to access a public IP from your work laptop that your neighbor could also access. Maybe we want a VPN or some sort of tunneling protocols built in to a VPN concentrator that then redirects your traffic to the cloud when you're reaching a cloud asset. Maybe we want that. Maybe we want dedicated private connections from our enterprise to the cloud. There's even a way to build IPsec tunnels from like a Cisco firewall or router to the cloud. As long as you have that outside IP, right? It's possible, IPsec. So that's what we're saying here is that customer to cloud connectivity, we're not worried about availability. That was built into cloud computing. That's one of the core tenets is that it's highly available as long as you have network access anywhere, broad network access. What we're talking about is how do we secure that connection? So it's the same things again, VPNs, IPsec tunnels, TLS tunnels, some sort of like policy-based routing that says go through here first, like maybe a CASB before you access the cloud services. And maybe it's not a one-size-fits-all. Maybe we have some SaaS applications that we don't care. Access it from anywhere because we're going to implement IAM and multi-factor authentication. So even if your neighbor can reach this public web address, that's a cloud service for our company, who cares? Because maybe you have to plug in a token that only you should have on you that shouldn't be duplicated and put in a PIN for that token to access this, which is kind of like what the Army did, right? It was like, well, OWA, it's public, who cares? And then they changed their minds and said, no, we want you to VDI into an Azure service to then access your email from home. It's crazy, but anyways. Okay, moving on. Cloud service integration. So enterprises rarely use cloud services in isolation. Cloud platforms must integrate with identity providers, monitoring system, DevOps pipelines, and third-party services. We don't ever do a green deployment of the cloud usually. Like if I'm using a startup, maybe that's the only time I can see where we start off in the cloud. But a lot of times these big enterprises move to it. They have their on-prem. They are already working with identity providers, maybe third-party apps that it was SaaS, but maybe they didn't consider it their own cloud tenant. And now all of a sudden they're introducing Azure Enter ID and Intune to like manage computers, remote workers. And so they're like, okay, now we need to integrate. Now we need to integrate our on-prem into the cloud. So now we have this hybrid model. Now we're exposing all these different APIs and touch points that we need to secure. Cloud service adoption. Cloud service adoption is not simply a technical decision. It is an organizational transformation that impacts security governance and risk management. And this is actually a good point because I don't know if you can tell, I love talking about the technical aspects of cybersecurity, but cybersecurity is mostly policy at the high level. Those people that are getting paid $275 grand to do cybersecurity, there's two options. Either you're some CISO manager somewhere in fucking meetings all day and writing policy, or you're some red hat super hacker that can do reverse malware engineering and analysis. It's like, that's the high paying cyber guys that are out there. And so cloud service adoption really matters to that high level, right? Well, if you're the CISO writing policy and you're an on-prem and you're making the decision to move to the cloud, that changes your entire risk and cybersecurity management framework because you've been building that based off the architecture you have now. And this isn't just a new server you're deploying or a new operating system you're trying. This is a total new enterprise architectural movement that may change your risk appetite, risk tolerances. You may need to look at different frameworks that relate to the cloud. Hell, you may start at that NIST publication, right? If you're working in the DoD, you want SaaS applications, the application you want to use has to be FedRAMP approved. So there's a lot of things that can happen with adoption of the cloud that if it's fast, you may be missing, or you may have a lot of exception to policies for a lot of the cloud stuff you're integrating and adopting. All right, quiz time. Okay, let me bring up my other screen here, guys, before we get started. All right, we are doing domain 2.5.2's quiz. We're going to do question 1 here. Just bring it up on my other screen. Okay. Question 1. A security team discovered that sensitive data was unintentionally exposed due to a misconfigured cloud storage service that allowed public access. No evidence suggests that an external attacker intentionally breached the system. Which cloud data security issue does this situation most closely represent? So you guys are quick. Okay, hold on. Let me see. You guys got C. Sensitive data was unintentionally exposed. Misconfigured cloud storage. Yeah, I mean, so it's between two, right? A and C. So yeah, let's go with C. Let's read this explanation here. So this scenario describes sensitive data becoming accessible to unauthorized users as a result of configuration error rather than intentional attack or data transfer. Data exposure specifically refers to a situation where data is unintentionally made accessible due to misconfigurations. Okay. So yeah, this is just unintentional. That's the key word here we're looking for in data exposure. All right, question 2. An organization stores highly sensitive customer data in a public cloud environment. Regulatory requirements state that the cloud provider must not have access to the data encryption keys under any circumstances. The organization also wants to ensure that if the data is deleted, it cannot be recovered by the provider. Which approach best meets these requirements? Okay, so we need to store sensitive data, whatever. We need to encrypt it, essentially is what this is saying. So regulatory requirements say that the cloud provider must not have access. The cloud provider must not have access to the data encryption keys under any circumstances. Well, damn, I'm going to change this question up. The keys, I guess you could host the keys locally and then always use them when accessing the cloud, but all right, whatever. The organization also wants to ensure that if the data is deleted, it cannot be recovered by the provider. All right, so this one's obviously customer managed encryption keys, but just to give you some real world guys, like if you have a storage account, like you need to encrypt, you still have to paste that key in, like at least the public key, I guess, into the cloud provider. So I guess this question kind of makes sense, but eventually it has to go to the cloud provider. That's where your stuff lives, but I'll keep this question, I guess. Yeah, it's B. Use customer managed encryption keys and destroy the keys when the data lifecycle ends. Yeah, I'm guessing we'll just assume this is talking about private keys, private encryption keys. Maybe it's symmetric, so maybe it's just one key. So okay, it's making a little bit more sense now as I talked it out. But okay, moving on. All right, question 3. An enterprise is designing security controls for a new cloud environment. The organization wants to prevent insecure configurations from being deployed while also ensuring that security teams are alerted if a misconfiguration still occurs. Which combination of control strategies best satisfies this goal? Wants to prevent let's see. An enterprise designing security controls for a new cloud environment. The organization wants to prevent insecure configurations from being deployed while also ensuring that security teams are alerted if a misconfiguration still occurs. Yeah, I don't like this question. But I think it's actually D, guys, because let's read it again, right? That prevent, I think is, I'm going to change this question around because it is a little confusing. The organization wants to prevent insecure configurations. So preventing insecure configurations is a proactive thing to do. And it's also preventative as well, but it's proactive. From being deployed while also ensuring security teams are alerted. That's detective. So this is the key one. Is that this doesn't detect at all, right? Oh, sorry. I'm highlighting on my other page. This doesn't detect at all, but we need to be alerted. Proactive controls can prevent things. Proactive controls can say, don't have insecure configurations. I don't like the way this is worded because it's intentionally trying to mislead you. So I'll probably change this one around. I'm going to reflag this. Look at this. Okay, we can adjust, right? This is the first time I'm running through this course, so. I know I made the questions, but sometimes you just working late at night. But yeah, it's gonna be D, and it's because it said alerting. But again, I don't know. I don't like. Let's see what this says. Proactive controls focus on reducing risk before systems go live by enforcing secure configurations, standardized templates, and security policies during design and deployment. Yeah, preventive controls alone may block certain actions, but do not necessarily identify misconfigurations that already exist. So. I guess that's the reasoning. I think I'm going to look at this one again because it's like intentionally misleading with that wants to prevent, right? If it said it wants to make sure there's or it's just that keyword. Like if it said the organization wants to ensure there's no insecure configurations, that'd make a little bit more sense, right? It's just that prevent keyword kind of fucks you up a little bit. All right, awesome. So now let's move on to our last section in domain 2. Where are we at here? Oh, cool, zero trust. Let's do it. Hold on, let me get a drink of this Celsius here. It was a long day at work today. We had to fucking just move on. Just a lot of Palo Alto. We're doing like Palo Alto SD-WAN right now, so. Okay. Let's talk about zero trust. So domain 2.6, this is given a scenario, integrate zero trust concepts into system architecture design. And this is going to be the whole thing we're going over. So zero trust architecture. So I've talked about this a lot. Zero trust has 3 core tenets that I need you guys to memorize. That is always assume breach, or maybe I'll write it out. Let's do this. So the 3 core tenets is always assume breach, always assume breach. 2, never trust, always verify. And then POOP, which is the principle of least privilege. Those are the core tenets that guide us in a architecture in our enterprise that gives what we call zero trust. And a lot of these things that achieve this is pretty much like multi-factor authentication, contextual awareness, and re-authentication and reauthorization anytime a subject accesses an enterprise object or resource, even if it's already been authenticated and trusted prior. Then always assume breach pretty much is our threat hunting and our continuous monitoring. So deploying systems into our architecture that monitor our entire attack surface based off organizational policy and really our industry compliance. And then with authentication, integrating a trusted system like PKI into it and doing good IAM management. So you see all these like things on the side here that are going into our zero trust architecture. And then we do a little diagram here. This control plane is everything we configure that's going to be applied. That's the policy decision point to our policy enforcement point, whatever that is. That could be a CASB. That could be a Palo Alto firewall. That could be a host of different authentication authorization services like Active Directory, Entra ID, Intune, TACX, Radius. And then the subject and object is whatever user, service account, or computer is trying to authenticate or reach or authorize any object on our network. So that's, we don't trust it. Even if it's already logged in, we don't trust you. We're going to re-authenticate you here to authorize you to access this enterprise resource. Okay, so let's just read some of these bullet points here. So traditional, let's see here. Traditional security architectures were designed around the idea of a trusted internal network and an untrusted external network. I've talked about this a lot, where we have that easy perimeter, that moat around our castle that was, you come sit at the HQ and you do your work and you go home and no one bugs you. Kind of nice. I want to go back to those days actually where you don't have Teams on your phone and people can hit you up after hours. It's like, oh, sorry, I'm off work. You better call the house phone and I may not pick up because that's my daughter's softball game, Be nice. I don't want to beat it over your head, but we got to talk about it because that's, getting away from that is what built zero trust architecture. So traditional security architectures were designed around the idea of a trusted internal network and an untrusted external network. So that is a firewall, your VPNs, your routers being at that perimeter, and that was your perimeter defense that got to track everything incoming and outgoing from your enterprise. And then what happened? Obviously, technology grew. We got past the internet bubble in the early 2000s. Cloud services started popping up, and then COVID happened in 2019, where all of a sudden every single enterprise had remote workers because the government said you can't be around each other. Once that happened, this really started becoming a thing, the zero trust architecture, which was already a thing prior to that, but with remote work and teleworkers and us deploying things to the cloud to make it our resources more highly available, we needed something that defined to us, no matter where your subject may be in the world, on-prem or off-prem teleworking, how do we monitor, log, protect, authenticate, and be in compliance? That's zero trust architecture. So zero trust architecture fundamentally challenges this assumption. Zero trust is based on the idea that no entity should ever be trusted automatically, regardless of where it is located. Every user, device, application, and system component must continuously prove that it should be trusted. Trust is not permanent and is not based on network locations. So even on-prem, we're going to re-authenticate you again. Okay. Let's go over some of these, core things in zero trust. Continuous authorization. I'm going to leave that up there actually, So in traditional systems, authorization usually happens once at the beginning of a session. That kind of is like domain joined computers where like you log in and then you're in, you're on the domain now, you're at your desktop, and that's it. A user authenticates, permissions are granted, and those permissions remain valid until the session ends. Zero trust rejects this model and replaces it with continuous authorization. So, something like this kind of goes and shows zero trust. We kind of already been doing this, but essentially we may have an authenticated user here that's authorized to this web server, authorized to this database. Nope, it's not, so we're going to block it. But if I want to talk to that web server again, like let's say I make the first session here, first session to the web server, and I get authorized to it. I get the permissions, right, set on my account. And then I start another session Should I go through this again? Yes, I should in Zero Trust. I need to be reauthorized again for that second session. That's essentially what we're talking about here, continuous authorization. That's fine. We can just clear all the drawings here. Okay. Now, context-based reauthentication. Talked about this. Do this a lot in the cloud with that P2 license I was telling you about in Azure. I don't know what AWS or GCP has. If I have something similar, we have to pay for it. But this is that contextual awareness that the banking industry has been doing forever, where you have a user behavior baseline that says you come in, you log in at 10 a.m. every day, you do your work till about 5 to 6, and maybe some after hours logins. And that's it. And you always come in, username, password, and multi-factor authentication, code on your phone, and that's it. But now all of a sudden, you're an authenticated user. We know you access our network, but it's, 1 in the morning. The location is Singapore, and you're trying to access the web server via FTP. So that's a sketchy login, and we're going to re-authenticate you. We're going to say, no. Thank you for logging into the system already, but I'm going to enforce a second factor again, and it's going to be different. Instead of a PIN, I may make you bring out your RSA token or do Face ID on the Authenticator app, plus a number that pops up on the screen that you have to type in. So that's context-based reauthentication. If you can think about what your bank does to you when you travel and you spend money and they make you verify, it's the same exact thing here, but you have to build it. That's the point of it. As an administrator, this doesn't just happen automatically because you want to do it. You got to go into your policy decision point, wherever that is, whatever that is, that's Intune, Enter ID, Active Directory, whatever it is, and configure that. And there's like levels to it. You could say extremely high risk or low risk. Is that what it is in Azure? Something like strict. This is like high strict, there's certain values you can add to it of how often you want to re-authenticate someone. Okay, Zero Trust network architecture. Now we're going to talk about segmentation in a traditional environment versus a cloud environment. So in a traditional environment, we have traditional segmentation using something like VLANs and access control lists. This is going to segment at the layer 2. And then we create these VLANs, and that subnet goes into like Microsoft sites and services that correlates to like an organizational unit. And you can apply GPU based on that sites and service, which is correlated to a subnet, which correlates to a VLAN, which correlates to an OU. All right. That's traditional segmentation. Now, micro-segmentation is more east to west filtering in the cloud. That's where we may have these microservices. You may have something like, VXLAN maybe in the data center where you're, geographically dispersed and still extending that layer 2, and we do what's called micro-segmentation. So this takes segmentation to a much finer level. Instead of separating large network zones, micro-segmentation applies access controls at the workload or application level, meaning I could have a VNet in the Azure East region with multiple subnets, and I could have VMs in a single subnet, and I could do application security groups on this VM talking to this VM, even though it's in the same subnet. So that's micro-segmentation. It's called like east to west because you put it on a diagram. That's kind of how it looks. Compared to like traditional segmentation, maybe north to south, where those VLANs all converge on some layer 3 device, like a router sub-interface, and then comes back down. Okay, VPNs in Zero Trust network architecture. Hold on. Okay, Zero Trust network architecture. So VPNs, a core component of it. A lot of times people, that same instructor I talk about a lot, John Saville, that does like the Azure stuff on YouTube, he talks about how a lot of people, they deploy VPN and they're like, Zero Trust. It's one component of it. And there's different ways to deploy VPN. It isn't a one size fits all. There's always on VPNs, there's split tunnel, full tunnel, there's remote access VPNs, and there's site to site VPNs. So traditional VPNs, just site to site, extend an internal network to remote users traditional VPNs extend the internal network to remote users or they do site to site. And then once connected, they just gain access to everything in the internal resources, everything in the enterprise. Oh, you connect to the VPN, you have access to everything. Always on VPNs improve security by ensuring that all traffic is encrypted, but they still rely on the idea of network level trust. In Zero Trust architectures, VPNs are typically used only as a transport mechanism, not as a primary access control solution. So what we're saying here is like let's say back in the day, a couple of years ago, VPNs got you into the network and you're good. You don't have to do anything else. But now we want VPNs that re-authenticate you, and they don't just give you, oh, you're authorized now. It's kind of like Cisco AnyConnect and SoftNet U. Like if we take our Nipper computers, we can plug them in a commercial, but then we have to connect to a VPN concentrator, and we have to select the location, and then it re-authenticates us. We have to put in our CAC pin again, even though we're already logged on. So that would be like an always-on VPN to even get you into the network, and then we still have to re-authenticate and reauthorize to access network resources. So modern zero trust designs favor identity-aware application-level access rather than just full network granted access. Okay, API integration and validation. So modern systems rely heavily on APIs to enable communication between applications, services, and cloud components. I don't want to beat your head on the APIs again. How many times do you think APIs have come up in this class, guys? I think this might be maybe the 10th time. And I'm just going strictly off the exam objectives, so it's funny. But it's the same thing, guys. If you have APIs and we're trying to implement a zero trust architecture, guess what? Every time you access that API, you may have to re-authenticate, and we need to continuously log and monitor that API so we can be aware of any denial of service attacks or any brute force attacks trying to access our backend API where maybe you need a key. All right, asset identification, management, attestation, which we talked about that already too. Zero trust depends on knowing exactly what exists in the environment. So you can't have good zero trust if there's a resource you don't even know about. There's some data, a service, a server, software laying out there that it's not on your asset inventory. You didn't network discover it through your Nessus scans or your SIEM systems. So you need to have good asset identification so you can be aware of the entire attack surface. So once assets are identified, they must be continuously managed. This includes tracking ownership, purpose, configuration, patch levels, and security status. And there's multiple different tools we can use to accomplish this. SIEM, MDM solutions, stuff like Intune. Then attestation is the process of verifying that an asset meets defined security requirements before it is allowed to access resources. A device may need to prove that it is properly patched, running approved software, and free from known compromise. Security boundaries. So security boundaries in a zero trust architecture exist in many different places. Now again, zero trust came about because of a lot of remote workers and cloud. So security boundaries could be internal on-prem on your enterprise between VLANs or even user to user, user to server, user to the internet. It could exist within the cloud between different cloud resources that may exist in different regions or different zones within the region or even different VPCs or different VNets within that zone and region. So let's go over what's on the slide here. So data perimeters. Data perimeters focus on securing the data itself rather than relying on network location. Essentially saying we don't care where it's located, we're gonna do full disk encryption. We're gonna implement the same IAM policy. Secure zones. Secure zones are controlled environments where sensitive operations or data processing occurs. Entry into these zones requires strong authentication, strict authorization, and continuous monitoring. Think of this as like a special access program, like a department, within your organization, where we actually implement even stricter access controls that may go beyond just company baseline policy. And then system components. So in zero trust architectures, each system component is treated as its own protected entity. Communication between components is explicitly authorized, authenticated, and monitored. All right, getting into some of our advanced networking now. Just one more slide. Okay. I'm going to try to keep this as simple as possible. And I need to correlate it to security because I would love to deep dive into this stuff because, again, I'm a senior network engineer for my day job. But when it says deperimeterization, this is just more of a zero trust architecture that says, hey, it ain't just your router that's the perimeter now. That may be connecting to an SD-WAN controller that's also now could be considered a perimeter, right? Because guess what? If they get into that vManage, which is not called that anymore from Cisco, they renamed it. Forgot. But if they get into that vManage, which controls all the edge nodes, that could be perimeter breach as well. So let's just go over what these technologies are and then again relate them to solid cybersecurity fundamentals that we need strong access controls against them. We need encryption and we need to understand how it changes our perimeters and how we need to look at our attack surface a little different than just a perimeter router, protect that. So a Secure Access Service Edge, so SASE, is a cloud-based model that combines networking and security services. So it pretty much does all those advanced security things. So, user behavior analysis, enabling AI machine learning to do data loss prevention and intrusion prevention system. It's a VPN concentrator. It allows remote access workers, all those advanced security techniques. Then also does SD-WAN, allows you to do bandwidth management, application service level agreements, allows you to gather telemetry. It's an all-in-one solution platform that, guess how you protect it? IAM. Strong authentication and access controls. And then within that device itself, you want to make sure that you're using everything you can to secure. So if you're building secure TLS tunnels, you want to make sure the basics are there, using the highest level of security you can. Just simple things like that. SD-WAN, SD-WAN, software-defined WAN, is essentially a single pane of glass where you have all these edge nodes that have multiple ISP connections that allows you to have actual application control across those multiple paths without asynchronous routing. So let's just read the slide. SD-WAN allows organizations to dynamically route traffic across multiple network paths while applying security and performance policies. So in zero trust environments, SD-WAN integrates with identity and security systems to ensure that traffic is both efficient and secure. And it is true, like when you're onboarding a device into like Cisco SD-WAN, you need like a certificate of authority that's trusted, and they need to authenticate and be trusted before they're allowed into that, SD-WAN environment. And SDN is just kind of like an umbrella term that says, hey, we're not doing traditional networking, we're doing software-defined networking where it's API-based, it's centralized control. We can centralize the logging, the monitoring, the upgrades, the updates, the route policy, and the security policy to all of our network devices in campus, such as switches, routers, firewalls, and access points. Okay, subject-object relationships. I already touched on this, but essentially any user, device, or service account that has to be authenticated and authorized to access some sort of object on the network, whether that be a shared drive, a database, a single file on a computer, that's a subject-to-object relationship. And that subject-to-object, the subject should always be untrusted, never trust, always verify, and should always have to pass through some sort of policy enforcement point before accessing that object, even if it was already trusted prior. So we need to define these relationships and enforce that principle of least privilege and make sure we're passing through some sort of policy enforcement point as a subject. Okay, let's do our quiz. Gotta do it in this browser. Okay, so finishing up domain 2 now. Domain 3, I need to go quicker because, we're on day 3, so let's see how much more stuff we have. I at least want to get to like this here, guys. Domain 3.6 today. So I'll go a little quicker after this. Okay. All right, question 1. A zero trust system requires every device to prove it is compliant with security policies, such as having current patches and approved software, before accessing internal services. What zero trust capability enables this verification? I'm thinking C or D already. Let me open up your chat, sorry. It says device, so that's why I'm going more D. Okay. Requires every device to prove it is compliant. Yeah, compliant. So when we're proving compliance from our laptops, our mobile devices, our computers, that's at a station. I don't even know if I'm saying that right. But yeah, that's D. Question 2. Write this out. A security architect is designing a zero trust system where access to sensitive resources can be reduced or revoked during an active session if risk conditions change. Which zero trust concept is being applied in this scenario? Access to sensitive resources can be reduced or revoked during an active session. Okay, if risk conditions change, that's conditional access. So we're saying, hey, Remember zero trust core principles. Never trust, always verify, right? So if you're still using something, what do we want to do in zero trust? Continuous authentication and authorization. So if something says, kind of meets that conditional contextual awareness threshold that says this looks sketchy, essentially it's all it's doing. It says this looks weird, this is beyond the behavior baseline, we need to re-authenticate or reauthorize you. So that concept here is continuous authorization. Yeah, that's a good way to look at it, Jeremy. If you're still using it, so that's continuous, right? You're continuously using it, and then this question saying, well, we kicked you off, we're making you re-authenticate or reauthorize, right? That's continuous authentication or authorization. Question 3. An organization replaces its traditional VPN-based remote access solution with a system that grants users access to only specific applications based on identity, device posture, and contextual risk, regardless of network location. Which architectural principle is this organization primarily implementing? So remember, zero trust came about because we didn't have that easy perimeter anymore. So they called that deperimeterization, and our network protocols followed suit. So yes, Masood, you are right. That is going to be A. Some good answers here, though, like C and D is not really like a zero trust concept. Like network segmentation, so yeah, VLAN isolation could be part of zero trust architecture, but microsegmentation and deperimeterization is kind of like the new things it introduced, I guess I should say. Not that we got rid of the old. So it's only between A and B here. So yeah, we're going to go with A, deperimeterization. Awesome. We got 100%. Let's go, people. Okay. I need to get into domain 3 now. We'll go over domain 3.1 and then we'll take our next break. Oh, that's the wrong one. Look, guys, we have one slide. JK. For some reason, I don't know what I did here. I copied 2 for some reason. This is the one that has our slides. Okay. All right, actually, before we do that, let's go to our Google Drive and let's take a look at our exam objectives here. Oh yeah, I forgot the preview sucks. You know, let's just download it. Make sure this works. Boom, there we go. So domain 3 is going to be 31% of the test. So that's technically our biggest domain, but if you come down here to it, this is security engineering. So we got to get through domain 3.1 all the way to 3.8. But you can see some of these bit pretty short. So that's why I was like, I want to get at least to domain 3.5 today because, or maybe all the way to 6 because, you know, this is easy. And then we just have domain 4, which is just 4 sections. So a lighter on domain 4. This is everything we got to get through in domain 3. So we're going to start here with domain 3.1. So let's get into it. And look, we're gonna go over a lot of shit kind of we already went over. Like we already went over SSO, but we're getting into the technologies that kind of enable that federation we talked about. More conditional access. That's crazy. And then, you know, more access control. So let's talk about it. Okay. Let me bring up my other screen here. All right, domain 3.1.1. Given a scenario, troubleshoot common issues with identity and access management, IAM. So we're going to go over subject access control and secrets management. So here is everything we're going to go over in this slide deck, everything in red. Okay, so user-based access control. So users are human subjects who authenticate to systems using credentials such as username, passwords, MFA, biometrics, or federated identity providers. User access issues are among the most common IAM problems encountered in enterprises. Essentially, all we're saying here is when we build IAM, is we're going to have services, users, and devices that all need their own IAM policies applied to them. Maybe they can all be under one, but usually we like to separate that. Like users are going to have more RBAC least privilege things, like a device that's doing like a domain join, we could apply a group policy to that computer that relates to like more of that computer's compliance rather than like access control, but it's still part of it. So a user may be denied access even though their credentials appear correct. This can occur when the user is not a member of the required group, does not have the appropriate role assigned, or is subject to a conditional access rule that blocks access. So when we start troubleshooting user access control, we go to that policy decision point. We go into that, well, one, honestly, if it's like we think it's a permission issue, from a cybersecurity perspective, we look at it like, well, maybe it's supposed to be like that. They can't access this. Well, let's go check their, I don't know, their AUP, their onboarding documents, what their role is, what they should have. And if they don't need access to this, get rid of this troubleshooting ticket and reply saying, hey, you need to maybe put in why you need access to this. Maybe there's something we don't know. Maybe some manager is going to approve it, and maybe we send it to that manager. So these user-based access controls probably will take up a bulk of your work, especially if you're sitting on like a help desk or you're a cybersecurity engineer that has to look at maybe ETPs for why this user needs to access something. Process-based access control. So processes are non-human subjects such as scripts, background jobs, scheduled tasks, and automation workflows. A lot of times, like I have this little script here. It's API, right? It was way longer. But it's to access a Google to run a authentication API to integrate it as an identity provider. I took this small snip. You guys see this? So when we're looking at security for process-based access control, you don't want to just like put your password right there in the code. You want to maybe reference like a key vault or something that's more secure. But these processes, these scripts have to be run by someone or something. So even if it's an automated script that runs from like an event scheduler or like a cron job, there still needs to be permission set on that script that will give it authorization. So whether it's a service account that we have to give permissions to that runs the script automatically, or it's like a cron job or a scheduled event, there's going to be some sort of elevation there to get this script to run, this process-based access control. So it's something we have to look at as well. And these failures, if like, let's say, got denied, may be logged differently. It may not go to the regular user, in a Linux server like var/log/like users or something like that. Okay, device-based access control, kind of talked about this. A good example of this is like when we implement network access control, like 802.1x, and maybe a device is in the wrong VLAN. So maybe it's meant to be in VLAN 12, and that port's on VLAN 14. You plug that computer in, a computer that's supposed to be part of VLAN 12, and it's all messed up. You're not going to get, access. It could be that it has an outdated certificate that we're using in our 802.1x radius environment. So it could be a certificate expiration issue. So in many enterprise environments, devices themselves have identities. That's laptops, mobile devices, servers, virtual machines, and they're all objects in Active Directory that could also get group policy applied to them as well. And they may authenticate using device certificates or be registered with an endpoint management system. So when troubleshooting device-based problems, it is necessary to verify device registration, certificate validity, and compliance status. Service-based access control. So services are applications or workloads that communicate with other services. In cloud and microservices architecture, service-to-service authentication is extremely common. Services typically authenticate using certificates, tokens, or managed identities. Biometrics, just some more basic of access control. Like in multi-factor authentication, we have 3 factors. That's something you have. So imagine that's your cell phone. You have an authentication app on there. Something you know. So that's something you create. Username, password, PIN. Something that you created. And something you are. And that's your biology. So that's the biometrics. So biometric authentication uses physical or behavioral characteristics to verify identity. Again, I don't need a deep dive too. It's Face ID, it's fingerprint as a way to authenticate. Okay, secrets management, tokens and certificates. So tokens are temporary credentials used for authentication and authorization, often in modern application environments. Tokens may expire, lack required permissions, or be issued by an untrusted authority. Certificates are used to establish trust and verify identities in secure communications. They are commonly used for HTTPS, device authentication, and service-to-service communication. Okay, secrets management. So if we have password or cryptographic keys, how do we manage them? So even though like in a modern architecture, we may like passwordless authentication, that may be something we want to do. Sometimes it just doesn't always work. Whatever the case, we need passwords. Maybe the burden's too high for passwordless authentication. We need passwords. And we need maybe cryptographic keys that we have to manage. You have to manage it securely. Have some sort of like key management software like a KMS, or if you have cryptographic keys, make sure you're hashing things. Make sure you're hashing passwords as well. Make sure you have good password policies, and just overall have good secrets management. If you do have passwords, maybe you want a single sign-on experience so a user only has one password to manage, and then couple that with multi-factor authentication to make it a little bit more secure. Okay, rotation and deletion. So rotation is the practice of regularly replacing secrets to reduce the risk of compromise. While rotation improves security, it can also introduce failures if not implemented carefully. We're just saying here, like, if you rotate a key, you also have to make sure you make it invalid. Then deletion. So deleting secrets without understanding dependencies can cause immediate failures. Secrets that are still in use should never be deleted without proper analysis. All right, and then conditional access. I talked about this so much. We'll talk about it again. So this user-to-device binding. So user-to-device binding restricts users to accessing resources only from trusted devices. Geographical, this is just saying company managed, like, hey, you can only access this resource from company managed device. We're not going to set up any way for you to do it from your personal computer. Geographic location, we could put some I don't want to say a fence, but yeah, geolocation that say, hey, in the continental US, you can only access this. Or you have to put in paperwork, or you have to put in something if you're traveling overseas and you want to do work overseas. Or if like companies making you do it, maybe they still make you put in something. Time-based access, there's like that rule-based access control, or maybe you have specific logon hours. Oh, cool, quiz time. Why did it go? Do I not have 3.1.2? What's going on here? There we go. Okay. Wait, what am I doing? I'm in 3.1.1. I don't know why I don't know. Okay, we'll move on. My ADHD brain. I don't know if you guys can tell that I have one. Sometimes it just goes a little crazy. Okay, so we're doing domain 3.1.1 quiz. Question 1. A cloud-hosted service suddenly begins failing to authenticate to another internal service, causing a partial outage. Investigation reveals that the service's authentication certificate expired earlier that day. No configuration changes were made to either service. What should have been implemented to prevent this outage? Okay. Let's read this again. All right. A service started failing to authenticate to another internal service. So still in the cloud, causing a partial outage. Investigation reveals that the service's authentication certificate expired earlier that day. Okay, so we know why that happened. No configuration changes were made to either service. What should have been implemented to prevent this outage? So we didn't re-get our certificate. We didn't redo it. We didn't do proper, I'm trying to relate this to the slides, proper rotation essentially. We didn't do proper rotation. So let's look at our answers here. So A, long certificate validity period. That would fix that problem, right? But that's not good security. We want, like actually nowadays, I think they said TLS, like X.59 certificates are going to rotate like every 3 months now. B, automatic certificate rotation with monitoring. Probably our answer there. Password-based authentication, no. Disabling certificate revocation checks would not help us at all. So yes, this one we're going to go with B. Question 2. We'll get to it. An organization recently rotated credentials used by an automated reporting script that pulls data from a cloud API. Shortly after the rotation, the script began failing authentication, even though the new credentials are valid and active in the secrets management system. Manual API access using the same credentials works correctly. What is the most likely cause of this issue? Okay, this is a hard one. An organization recently rotated credentials used by an automated reporting script that pulls data from a cloud API. Or whatever. So we have a script. It's a process-based access control, and we rotated credentials, whatever that means. API key, client ID. It failed, but the new credentials are valid and active in the secrets management system. So we're pulling them maybe from that secrets management system. You know what? It's so funny. This is B. This is exactly what I just showed you guys on that image. And I didn't even mean to do that. Go back to the slide. Remember this one? This, and I was like, hey, don't do this. That's what's happening, I think. It's like, hey, you're actually not probably grabbing it from the secrets management every single time. You probably grab it one time and then puts it in this variable, and then that variable doesn't change because you don't recheck the secrets management system. So yeah, I think it's going to be B. The script is using cache or hard-coded secret. Even though it should be reaching out to a system to get it each time, it probably, your coding's fucked up, the code's fucked up, where it actually cached it or keeps using it after it reached out the first time and never reached out again, which, that's like the logic. I'm trying to think. It wouldn't be like an if, a for loop. Anyways, moving on. What the hell? Close. Hold on, guys. Okay. Question 3. A user reports that they can successfully authenticate to the corporate identity provider, but are denied access to a critical internal application when logging in from their personal laptop. The same user can access the application without issue from a company-issued device. So they can get into it with the company-issued device. They can't get into it from their personal. What is the most likely reason for this behavior? So A, the user account is missing required group membership. No, because it works on a company device. The application requires biometric authentication. Nothing was mentioned about that being a failure. C, user to device binding is enforced for the application. Probably that, which I love user to device. It just means company managed, whatever. The user's password has expired. No, because it can authenticate. Probably agent installed. Yeah, probably like some MDM. Like if you ever use Microsoft Intune, it's like only this user, can be on this laptop, whatever. But yeah, C, user to device binding is enforced for the application. Awesome. We got 100%, guys. Let's go. Okay. You answered 100% correctly. Alrighty. Let's go ahead and let's take another break. When we come back, we'll continue on with domain 3. I got my timer up. There we go.